Hi, folks. Welcome to 3.7 Rational Functions. Now, in the previous part, we talked about something called reciprocal functions and added that to our list about parent functions and their graph transformations. But in this next part of 3.7, we're going to talk about rational functions in general. Okay, so the stuff we learned before is like a very special case, and what we're talking about now is a more general case about all rational functions. Now, you might be sitting here saying, what is a rational function and why don't we have what we know and what's new? Well, I thought I'd mix it up a little bit, so here we go. Our rational functions, we're going to read through this definition together, okay? Because I think even though these days it's not as common to have to read a textbook, I still think it's really useful to learn how to read different kinds of language, right? And mathematics is one of those types of languages. So a rational function is a ratio of two polynomial functions, right? And so this word ratio here, you may actually see part of it in rational, right? So a rational function is the ratio of two polynomial functions. And in general, we write rational functions like this, okay? So if f of x is a rational function, then we can say that it is the ratio of p of x to q of x. In other words, we're saying some polynomial p divided by another polynomial q. The only thing we have to add here is that that polynomial in the middle, or in the bottom, it cannot be equal to 0, okay? So this is a polynomial. This is another polynomial. And when we take their ratio, we get this rational function. Okay, and so the ratio is really this part right here, that division. All right. Now, in this class, we're going to be talking mostly about the equation and the graph and how we can look at an equation and know what it's going to be on the graph, and also look at the graph and see how we get the equation. All right. There's going to be three main things, and actually two main things, but there's three different parts to them. We're going to look at something called end behavior, which we've talked about in this chapter already, and then something new called discontinuities, right? So talking about end behavior and discontinuities. And we want to be able to find these things from an equation and from looking at a graph, right? So let's get started with this end behavior, right? End behavior, it turns out that when we're looking at the ends of functions, a few things can happen, okay? But in this particular family of functions, rational functions, what we want to focus on is whether there's a horizontal asymptote or not, okay? And so if we think back to our reciprocal function, we had something, and I'll draw a little picture right here for us. For our reciprocal functions, we had a graph, right? And we had sort of two branches, one over here and one over here, right? And one of the things that we had indicated on our graphs was that we had this horizontal asymptote, okay? And so because it's such a popular characteristic of a lot of rational functions, it's something we look for in whether we have it or not, okay? That's what we distinguish. So a horizontal asymptote of a rational function can be determined just by looking at the degrees. Oh, so good thing earlier in chapter 3, we talked about how to find the degrees of polynomials. All right, so we're looking at the degrees, but the degrees of what? We're looking at the degrees of the numerator, or our p of x, and we're looking at the degrees of the denominator, or our q of x. All right, so in fact, I'm going to add that onto this definition that p of x is our numerator, and this q of x is our denominator, okay? All right, so if the degree is of the numerator is less than the degree of the denominator, it turns out that we end up with a horizontal asymptote at y equals 0. And we can actually see this by going back to that reciprocal function we looked at. That equation was f of x equals 1 over x, right? What's the degree of the top? It's actually 0 because it's secretly 1 x to the 0. Well, what's the degree of the bottom? 1. 0 is less than 1, which is why this reciprocal function that we were looking at had a horizontal asymptote at y equals 0. Okay. Now, what happens if we flip-flop that? Okay. And what I mean by that is the degree of the numerator is greater than the degree of the denominator. All right. Then it turns out that there's no horizontal asymptote, right? Another way of saying that is we have a slant asymptote. It's on some sort of a diagonal. And a good example for this second one might be something like this. A rational function where the degree on the top is bigger than the bottom. X squared has degree 2. 1 has degree 0. This is really the same thing as saying x squared. And we know that the end behavior of rational function x squared, well, that just looks like this. So our end behavior is up, up. That doesn't flatten out at all, right? It goes up and it goes up. But a horizontal asymptote would mean the ends go kind of flat, right? All right. One last case. The degree of the numerator is equal to the degree of the denominator. Now the degrees are the same. Well, it turns out that the horizontal asymptote is at the ratio of the leading coefficients. Oh, good thing we talked about leading coefficients, right? And how to find where they are. Let's do a quick example of this one. Okay, so let's say that we had f of x equals 3x cubed over 4x cubed, right? This p of x is a degree 3 polynomial, and this q of x is a degree 3 polynomial, same degree. But also, if I have x cubed divided by x cubed, those can reduce, and I just get 3 over 4. But what that means is this is actually our horizontal asymptote. Okay, so we end up with a function that completely flattens out when we get to the ends. All right, so that's our end behavior case, all right? Now, the second thing that I want to talk about in terms of rational functions is B and C collectively, they talk about something called the discontinuity. And what we're going to talk about is 2 different types of discontinuities, okay? We're going to talk about one type where we end up with a number divided by 0. And we're going to talk about another case where we end up with 0 divided by 0, okay? So it turns out that when we have a number divided by 0, all right, we end up with something called a vertical asymptote on our graph. So if we see a number comma 0, a number over 0, we end up with a vertical asymptote. Okay, so example. Let's say I had a rational function. It's some sort of ratio, right? And I have 1, that's a number, over x minus 5. Now, when we think back to our previous section, we saw that this minus 5 meant that we moved our graph to the right 5 units. And if we were to sketch a picture of this function, we would end up with I think I used green, a vertical asymptote at x equals 5. Our horizontal asymptote would stay the same at y equals 0. And then our graph would be here and here. Okay. Well, look at what we have when the denominator equals 0, or when x minus 5 equals 0, or when x equals 5, we have this vertical asymptote. Okay. So what I'm saying is we could have just looked at this equation and said x minus 5 equals 0. That means at x equals 5, we have a vertical asymptote. Okay, so pretty powerful there. Another example might be we have something like this. Let's say we have another rational function, okay? And we have 2 minus x over 3x plus 1, okay? 2 minus x over 3x plus 1. Now, anytime the denominator equals 0, I'm going to end up with a vertical asymptote, okay? So I'm going to take my denominator, and I'm going to set it equal to 0, and I'm going to solve for x. There is a vertical asymptote for this picture at x equals -1/3. All right. Last case here. We're going to talk about discontinuities, but what happens if we have a 0 on the top and on the bottom, like at the same number? Okay, that's going to be a different case. It turns out that when we end up with 0 on the top and the bottom, we end up with a hole in our function, not a vertical asymptote. Right? So what do I mean by that? Example. F of x equals x minus 3 over x minus 1 times x minus 3. Okay. Now I'm going to go ahead and graph this on Desmos. All right. So if you have a phone or a computer or a tablet, you can go ahead and go to Desmos. And it looks something like this. All right. And on this app, you can actually use it to graph things. All right. So all I would need to do is type in the equation. So x minus 3, close it, divided by x minus 1 times x minus 3. Okay. So I've got my function here. Now, I noticed that if I put 1 in for x, that my denominator is going to go to 0. And that's matches with what I see here, because at x equals 1, that blue line is actually a vertical asymptote. Okay, so x minus 1 is only on the bottom. It's not on the top. That gives us the vertical asymptote. But what is this hole that I'm talking about? Well, let's see. What number can I plug in to make the top and the bottom equal to 0? Well, I can plug in 3. When I plug in 3, I'm going to end up with 0 on the top and 0 on the bottom. So let's zoom in and see what's happening at 3. Okay, and at 3, if I click on this, I can actually see what numbers the function actually is. Let's see what happens when I get to 3. All right. You see that? There's a little open hole on the function. And in fact, it tells us 3 comma undefined. That's what a hole looks like in our function. Okay, so let's go back to the notes for a moment. This graph, all right, let's sketch it for ourselves so that we have something to remember. Oh, that's not a very straight one. All right. Now, I happen to know just from my picture that there was a vertical asymptote at 1, but I also could have known that because only that 1 only makes the denominator 0, right? So this is actually at x equals 1. And then the way I would draw this, let me put in my horizontal asymptote of y equals 0. The way I would draw this is I would draw this branch like normal, but then I would draw this branch like this, whole, and keep going. Okay, so I know it doesn't look like it on Desmos until we zoom in and we see that one spot, but when we draw them, we want to make sure that we make the hole very clear. Okay, so the reason again why there is a hole here is because we have x minus 3 on the top and x minus 3 on the bottom. That gives this hole right here. Okay. All right. So that's a brief overview. Let's put this all on one page here. This is a brief overview of 3.7, part 2. And in our next video, we're going to take a look at an example where we work through a whole problem like this. Okay. So I'll see you back here for part 2.